Hi folks, welcome back to Physics with Captain Rod. I'm making this video to provide an example of how to analyze rotational motion. So what we're looking at here, imagine we've got this car booking along here. And imagine that this car driver applies the brakes in such a way that the car goes from 60 mile per hour to 0 mile per hour in a time frame of 10 seconds. And what we're ultimately going to try to calculate is the angular acceleration of the tire and the change in theta here, how many times the tire went around basically while this was occurring. So before we talk about the rotational motion of the tire, I'm going to start by looking at the translational motion of the car. So if I were to start with a velocity graph for that car, all right, at t equals 0, the velocity is 60 mile per hour. Now I want units to be nice and consistent here, and I have the car's diameter written here in feet, or I'm sorry, not the diameter of the car, but the diameter of the tire. So we're going to want that velocity in feet per second. I've already done the unit conversion to calculate that velocity in feet per second. If you're not familiar with unit conversions, you can go back. I've got several videos on how to convert units. So when the car first applies, or I'm sorry, when the driver first applies the brakes, the car's going 88 feet per second. And then 10 seconds later, the car's not moving at all, so we'd say its velocity is 0. And if we make a constant acceleration assumption, this would give us a linear curve. Now, the reason I wanted to get that curve is this. The distance, or the delta x, traveled by the car can be found by this area right here. And I'm going to go ahead and do that because I'm going to need it for the rotational part of it. So that distance is going to be 1/2 times 10 seconds times 88 feet per second. And this ends up being, I think, 440 feet. Now, I don't need it right now, but if I wanted it, I could get the acceleration of the car easy enough by rise over run. That'd be negative 88 or over 10, or in other words, negative 8.8 feet per second. But all right, now that I've got that distance, all right, now I'm going to, oops. What I wanted to do here is move that stuff over and give myself a little more room. I guess I'll do this. So I'm just going to take this work. Just move it over to the side a little bit. All right, now what I'm going to do is I'm going to now analyze the motion of the tire, the rotational motion of the tire. And I'm going to start with an angular velocity graph that describes the tire. Now, for analyzing the tire, what I'm going to imagine here is this. Just imagine the car just sitting put and the tire rotating at whatever rate it's going at. It's important to realize that the distance that a point on the tire would move around in a circle would be the same as the distance traveled by that car. So that distance has to equal 440 feet. And what that's going to allow me to do is calculate how many times that tire went around. So I'm going to calculate one circumference. That's equal to 2 pi r, or 2 pi times 1 foot, which is 6.28 feet. Now, the 6.28 feet means that every time the tire goes around once, the car is going to move forward by 6.28 feet. So I'm going to put 6.28 feet per revolution. Now what I'm going to do is I'm going to take this 440 feet and divide it by 6.28 feet per revolution. And this number is going to come out in units of revolution. So it's going to tell me how many times that tire went around. And I get 70 revolutions. So right there's my change in theta. And I could multiply it by 2 pi if I wished to calculate that in radians, but I don't think I need to do that at this instant in time. Okay. Angular velocity of the car per unit time. So although I could pretty easily calculate it, for right now I'm just going to say that the angular velocity is some positive value. I'm going to call that the initial angular velocity. And then I know after 10 seconds, we're going to be here. I know the tire's not rotating anymore. And again, with a constant acceleration assumption would also mean this curve would be linear. Now, angular velocity is equal to change in theta over change in time. So you'll notice that your change in theta is equal to your angular velocity times your change in time. On this graph, the angular velocity is this dimension and the change in time is this dimension. So this area here, the area of the triangle, is going to give me my change in theta, which I effectively know. So our change in theta, which is going to be 70 revolutions, however at this point I'm going to go ahead and convert that to radians, times 2 pi radians per revolution. Now this is going to give me my change in theta in radians, is going to equal the area bound within this curve, which is going to be 1/2 times 10 seconds times what I'm going to call the omega initial, or the initial angular velocity in radian per second. And this equation can be solved for the initial angular velocity. So let's see what I get out of that. I get about 87.92. Let's just call that 88. We'll say approximately 88 rads per second. Now I know that when you look over here you'll say, oh well, that's the same as the speed of the car. Well, that's only because the radius of curvature here was 1 foot, right? And that's because I chose 2 foot for the diameter. Had this been any other number in the universe here, these would not be the same. So don't be mistaken by this into thinking that this translational speed is the same as this angular speed, because that's just coincidence. That's only because the value I chose here has a 1 foot radius. All right, so the initial angular velocity of the car, or I'm sorry, of the tire, 88 radian per second. The angular acceleration is change in angular velocity over change in time. Now, as far as this graph is concerned, that's slope. So if I use these 2 points here, our rise, if you will, is this, which is going to be minus 88 radian per second, and the run is this, 10 seconds. So the angular acceleration is going to be minus 88 rad per second over 10 seconds, which is minus 8.8 rad per second squared. And again, that R standing for rad or radian. So there is the angular acceleration of the tire. It came out negative. The negative sign does not exactly mean because the rotation rate is slowing down, right? Here's what it means. When I made my velocity graph, at t equals 0, I put a positive value here, meaning that I have defined clockwise as positive for this problem. And the angular velocity is in fact decreasing, which means the angular acceleration is in the opposite direction, or in fact counterclockwise. It is actually possible to have, in this case, a negative angular acceleration and have the angular velocity be increasing in magnitude. And if you'll humor me at the end of this video for just a little further, you know, imagine that this driver, and again, don't try this at home, but rather than applying the brakes, somehow manages to get this car out of forward and into reverse and gives it the gas or something. You know, it is possible that the car would slow down, stop, and then start accelerating the other way. And what would happen is this curve would just keep going down like this. So again, the point of the video here is not subtle things about vectors and directions, just generally how do we analyze the rotation of a system. And again, I like to do it graphically. So here to the left of this line here, we were analyzing the translational velocity of the car. To the right hand side, this graph is for analyzing the rotation of the tire. Hope this video helps. Have a great day.